Welcome to the Nocturnal Astronomer, where we explore the vast mysteries of space in a way that helps you drift peacefully into sleep. I'm your host, Atlas Reid, and tonight we're tackling one of the most mind-bending concepts in all of physics, the multiverse theory. Now, I know what you're thinking. The multiverse sounds impossibly complicated, like something only brilliant scientists with multiple degrees could possibly understand. But here's the beautiful truth: every complex idea in the universe can be broken down into simple, everyday concepts that anyone can grasp. Think of it this way. Imagine you're looking at a massive, intricate painting from just inches away. All you see are confusing brushstrokes and colors that make no sense. But step back far enough, and suddenly the whole picture becomes crystal clear. That's exactly what we're going to do with multiverse theory tonight. We'll step back from all the intimidating mathematics and technical jargon and see the elegant, simple picture underneath. By the end of our journey together, you'll understand not just what the multiverse is, but why some of the smartest people on Earth believe it might actually exist. We'll explore different types of multiverses, from the infinite cosmic bubbles to quantum realities that split every moment. And we'll do it all using ideas as familiar as soap bubbles, infinite libraries, and choosing what to wear in the morning. If you enjoy these relaxing deep dives into cosmic mysteries, please give this video a thumbs up and consider subscribing to join our growing community of nighttime space explorers. And here's something fun. In the comments below, tell me about the most interesting decision you made today, because as we'll discover tonight, in some parallel universe, you might have made the complete opposite choice. Let's dive in. To understand the multiverse, let's start with something beautifully simple: bubbles in a bathtub. Picture yourself relaxing in a warm bath, surrounded by countless soap bubbles floating on the surface. Each bubble is its own little world, complete and separate from all the others. Some bubbles are large, some are tiny, some last for minutes, others pop immediately. Each one contains its own air, its own thin walls, its own brief existence. Now, expand this image in your mind. Instead of soap bubbles in your bathtub, imagine cosmic bubbles floating in something far more vast than we can picture. Each bubble is an entire universe, complete with its own space, time, matter, energy, stars, planets, and perhaps even beings like us wondering if they're alone. This is the essence of multiverse theory, the idea that our universe, everything we can see and touch and measure, is just one bubble among countless others. But here's where it gets even more interesting. Just as no two soap bubbles are exactly identical, no two universes in a multiverse would be exactly the same. Some might have different physical laws. In one universe, gravity might be stronger, making planets smaller and denser. In another, the speed of light might be different, changing how stars form and shine. Some universes might be filled with matter we've never seen, while others might be nearly empty expanses of space and time. The beautiful thing about this bubble analogy is that it helps us understand something that sounds impossible: infinity. Just as you could theoretically keep adding soap bubbles to your bath forever, the multiverse could contain an infinite number of universes. And in an infinite collection of universes, every possible variation of reality would exist somewhere. This isn't science fiction or philosophical speculation. These ideas come from our best understanding of physics, from equations written by scientists like Albert Einstein and Stephen Hawking. The mathematics of cosmic inflation, quantum mechanics, and string theory all point toward the possibility that our universe is just one among many. Scientists have proposed several different types of multiverses, each arising from different areas of physics. Some come from the idea that space itself is constantly expanding and creating new regions that become isolated from each other. Others arise from quantum mechanics, where every quantum event creates branching realities. Still others emerge from string theory's extra dimensions. What makes multiverse theory so compelling is that it solves some deep puzzles about our own universe. Why do the fundamental constants of physics seem perfectly tuned to allow matter, stars, and ultimately life to exist? In a multiverse, there would be countless universes with different constants, and naturally, we find ourselves in one where the conditions happen to be just right for our existence. Imagine you're holding a balloon that never stops expanding. You draw a mark on the surface with a marker, and as the balloon inflates, that dot gets carried further and further away from other dots you might draw. Now picture this happening not with a simple balloon, but with space itself, stretching and growing at an incredible rate. This is cosmic inflation, and it gives us our first type of multiverse. In the early moments after the Big Bang, space expanded faster than the speed of light. This might sound impossible, but remember, it's not matter moving through space, but space itself stretching. Imagine the surface of our balloon expanding so quickly that distant parts of it lose all connection with each other. Light from one region can never reach another region because the space between them is growing too fast. Here's the remarkable part. According to our best theories, this inflation never completely stops everywhere at once. While it ended in our observable region about 14 billion years ago, allowing matter and energy to cool and form atoms, stars, and galaxies, it continues in other regions, constantly creating new volumes of space. Think of it like popcorn kernels heating in a pot. Each kernel pops at a slightly different time, creating individual pieces of popcorn, but the heating process continues, creating new popped kernels continuously. In cosmic inflation, each popped kernel becomes a separate universe like ours, with its own Big Bang, its own space and time, its own physics. These pocket universes, as physicists call them, would be separated by regions of still inflating space. The distances between them would be so vast that they could never interact or communicate with each other. Each would be causally disconnected, meaning that events in one could never influence events in another. But here's where it gets mind-boggling. If inflation creates an infinite number of these pocket universes, and if the laws of physics allow for only a finite number of possible arrangements of matter and energy, then eventually, every possible configuration must repeat. This means that somewhere in this infinite cosmic multiverse, there would be another Earth, another solar system, another you reading these exact words. In fact, there would be infinite copies of you, with every possible variation in your life playing out somewhere. Versions where you made different choices, where you became different people, where history unfolded differently around you. Some versions would be nearly identical to you, differing in only the tiniest details. Others would be dramatically different, living completely alternative existences. This idea comes directly from mathematical probability. In an infinite collection of finite possibilities, every possibility must occur, and must occur infinitely many times. It's not speculation or imagination, but a logical consequence of infinity combined with the finite ways that matter and energy can arrange themselves according to the laws of physics. Every morning when you wake up, you make choices. Coffee or tea? Blue shirt or red shirt? Take the highway or the back roads to work? We experience these as single decisions with single outcomes, but quantum mechanics suggests something far more extraordinary might be happening. According to the many worlds interpretation, every quantum event, every moment where multiple outcomes are possible, reality splits into parallel branches, each containing a different outcome. To understand this, let's think about something simpler than morning choices, flipping a coin. In our everyday experience, you flip the coin, it lands either heads or tails, and that's that. But at the quantum level, the fundamental level of reality, particles exist in what physicists call superposition, meaning they can be in multiple states simultaneously until something observes or measures them. Imagine the coin flip differently. Instead of landing on either heads or tails, picture reality itself branching at the moment of the flip. In one branch, the coin shows heads, and a version of you sees heads. In the other branch, the coin shows tails, and another version of you sees tails. Both versions are equally real, equally valid, existing in parallel universes that have split off from each other. This branching happens not just with coin flips, but with every quantum event in the universe, billions upon billions of times every second. Every time a particle can go left or right, every time an atom can decay or remain stable, every time any quantum possibility resolves itself, reality branches. The result is an ever-expanding tree of parallel universes, each containing slightly different versions of everything that exists. The remarkable thing about this quantum multiverse is that all these parallel realities are equally real. There's no original universe and no copies. Each branch contains conscious beings who experience their reality as the only reality, completely unaware of all the other branches where other versions of themselves are making different experiences. This helps explain one of the strangest aspects of quantum mechanics, why quantum events appear random to us. When we measure a particle's position or momentum, we see what appears to be a random outcome. But in the many worlds interpretation, it's not truly random. Every possible outcome actually happens, but we only become aware of one of them because that's the branch of reality we find ourselves in. Think about your own life from this perspective. Every decision you've ever made, every accident you've avoided or encountered, every person you've met or missed meeting, and the quantum multiverse, all the alternative versions played out. There are versions of you who made completely different choices at every major crossroads of your existence. Scientists who support this interpretation point out that it requires no additional assumptions beyond what quantum mechanics already tells us. The mathematics of quantum theory naturally describes these branching realities. We simply do not usually think about it this way because we only experience one branch at a time. Mathematics is often called the language of the universe, but what if it's more than that? What if mathematics doesn't just describe reality, but actually is reality? This leads us to one of the most profound ideas in modern physics, that every mathematically consistent structure exists as a physical reality somewhere in a vast multiverse of mathematical possibilities. Think about numbers for a moment. The number 7 exists in a very real sense, even though you can't touch it or put it in a box. You can have 7 apples or 7 stars, but the number 7 itself is an abstract mathematical object that exists independently of any physical representation. Now extend this thinking. If mathematical objects like numbers and geometric shapes can exist in this abstract but real way, what about more complex mathematical structures? Consider the equations that describe our universe. Einstein's field equations describe gravity and spacetime. Schrödinger's equation describes quantum mechanics. Maxwell's equations describe electromagnetism. These aren't just useful tools for prediction, they appear to describe the actual structure of reality itself. But here's the profound question: why these particular mathematical structures and not others? The mathematical universe hypothesis suggests that all mathematical structures exist as physical realities. Our universe, with its particular laws of physics, corresponds to one specific mathematical structure. But there could be other universes corresponding to other mathematical structures, each with different physical laws, different dimensionalities, different ways that matter and energy behave. This connects to string theory, one of physics' most ambitious attempts to describe all fundamental forces and particles in a single framework. String theory suggests that the most basic building blocks of reality aren't point particles but tiny vibrating strings. The different ways these strings can vibrate correspond to different particles, electrons, quarks, photons, and so on. But string theory comes with a catch. For the mathematics to work consistently, it requires extra spatial dimensions beyond the three we experience. These extra dimensions must be curled up so small that we can't detect them directly. And here's where it gets interesting. There are an enormous number of ways these extra dimensions can be configured. Each different configuration creates what physicists call a different vacuum state, essentially a different possible universe with different physical laws. The number of these possibilities is staggering, estimated to be around 10 to the power of 500. This collection of all possible string theory universes is called the landscape, and it represents another type of multiverse. In this string theory multiverse, our universe would be just one point in this vast landscape of possibilities. Other universes might have different particles, different forces, different numbers of dimensions that we could actually move around in. Some might be completely empty, others might be filled with exotic forms of matter and energy that don't exist in our reality. The profound implication is that mathematics itself might be the deepest reality, more fundamental than matter, energy, space, or time. Physical universes might be mathematical structures experiencing themselves from the inside, and consciousness might be the way mathematical patterns become aware of their own existence. Imagine you're looking at a hologram, one of those shimmering images that appears three-dimensional even though it's printed on a flat surface. The remarkable thing about holograms is that all the information needed to reconstruct the three-dimensional image is stored on the two-dimensional surface. Even more amazingly, if you cut the hologram in half, each piece still contains the complete image, just with less resolution. This strange property of holograms has inspired one of the most revolutionary ideas in modern physics, the holographic principle. This principle suggests that all the information contained in a volume of space can be represented on its boundary, just like a hologram stores three-dimensional information on a two-dimensional surface. Applied to our universe, this means that everything we experience as three-dimensional reality, all the matter and energy and space around us, might actually be information encoded on a distant two-dimensional surface. We would be like characters in a holographic projection, experiencing ourselves as fully three-dimensional beings while actually being patterns of information on a cosmic boundary. This leads to a fascinating type of multiverse. If our universe is essentially information encoded on a boundary, then there could be many such boundaries, each encoding its own universe. These holographic universes might exist in higher dimensional spaces, with each lower dimensional boundary giving rise to what its inhabitants would experience as a complete, consistent reality. Think of it like this. Imagine a library filled with an infinite number of books. Each book is written in a special code that, when properly decoded, creates an entire virtual universe complete with space, time, matter, energy, and conscious beings who experience their reality as completely real. From their perspective inside the story, they are living in a three-dimensional universe with a rich history and complex physical laws. But from our perspective outside the book, they are patterns of information on pages. The holographic principle also connects to black holes in remarkable ways. Stephen Hawking and other physicists have shown that black holes contain entropy, a measure of information, proportional to their surface area rather than their volume. This suggests that the information falling into a black hole is somehow stored on its two-dimensional event horizon rather than in its three-dimensional interior. This creates yet another type of multiverse possibility. Every black hole might be a portal to another universe, or might itself contain an entire universe encoded on its surface. The information that falls past the event horizon doesn't disappear, but becomes part of a holographic encoding of reality that exists from the black hole's perspective. Some physicists have even suggested that our own universe might exist inside a black hole in a higher dimensional space. From the outside perspective, we would be information patterns on the black hole's event horizon. From our inside perspective, we experience a rich, expanding universe with billions of galaxies and a long cosmic history. The implications stretch even further. If reality is fundamentally information, then the distinction between simulated and non-simulated universes becomes meaningless. A sufficiently detailed simulation would be indistinguishable from reality to its inhabitants, not because the simulation is fooling them, but because there would be no fundamental difference between simulated and non-simulated existence at the deepest level of information processing. You might wonder, if these parallel universes and alternate realities exist, shouldn't we be able to detect them somehow? After all, science is about observation and evidence, not just beautiful mathematical theories. The truth is that multiverse theories are challenging to test directly precisely because, by definition, other universes are separated from ours in ways that prevent direct communication or observation. However, scientists have identified several potential ways that multiverse theories might leave observable traces in our universe. Think of it like detecting a hidden room in your house. You can't see into the room directly, but you might notice that the house's architecture doesn't quite add up, or you might hear sounds coming from spaces that shouldn't exist. One of the most promising areas involves the cosmic microwave background, the afterglow of the Big Bang that fills all of space. This radiation carries a detailed imprint of the early universe, like a baby photograph of the cosmos. If our universe had collided with another bubble universe in the early stages of cosmic inflation, such a collision might leave distinctive marks in this background radiation. Teams of scientists have searched for these collision signatures, areas where the cosmic microwave background shows unusual patterns that could indicate our universe bumped into a neighboring one. While no definitive evidence has been found yet, the fact that we know what to look for represents genuine scientific progress. The absence of such signatures also tells us something. If bubble universes exist, they're either very rare in our cosmic neighborhood or the collisions happen in ways that don't leave detectable traces. String theory multiverses might be detectable through particle physics experiments. If extra dimensions exist and are configured in specific ways, high-energy particle collisions might produce unusual results that reveal information about these hidden dimensions. The Large Hadron Collider and future particle accelerators continue searching for such anomalies. Quantum many-worlds theories make different predictions about quantum mechanical measurements than some alternative interpretations. While we can't directly observe parallel branches, careful experiments involving quantum superposition and measurement might eventually distinguish between different interpretations of quantum mechanics. The holographic principle has led to concrete mathematical relationships that can be tested. Physicists have found that certain calculations in quantum field theory match exactly with calculations in string theory when applied to holographic boundaries. These mathematical concordances provide strong evidence that the holographic principle captures something real about the nature of space, time, and information. perhaps most remarkably, the fine-tuning of physical constants in our universe provides indirect support for multiverse theories. The values of fundamental constants like the strength of gravity, the mass of the electron, and the rate of cosmic expansion appear to be precisely calibrated to allow the formation of atoms, stars, planets, and ultimately life. In a single universe, this fine-tuning would be an extraordinary cosmic coincidence. But in a multiverse containing countless universes with different physical constants, it becomes statistically inevitable that some universes would have the right values for complexity and life to emerge. We find ourselves in one of these rare, habitable universes not because of luck or design, but because that's the only type of universe where observers like us could exist to notice the fine-tuning in the first place. As we near the end of our cosmic journey tonight, let's pause to consider what multiverse theory means for the deepest questions humans have always asked. If parallel universes exist, what does that tell us about the nature of reality, consciousness, identity, and our place in the grand scheme of existence? First, consider the question of uniqueness. Throughout human history, we've gradually discovered that we're less special than we initially thought. We learned that Earth isn't the center of the universe, that our solar system is one among billions, that our galaxy is one among trillions. Multiverse theory represents the ultimate extension of this cosmic humility. Not only are we not unique in our universe, but our entire universe might not be unique either. Yet paradoxically, this makes existence more precious, not less. If every possible version of reality exists somewhere in the multiverse, then the specific combination of events, choices, and circumstances that led to this moment, to you hearing these words right now, represents something infinitely valuable. This exact configuration of matter, energy, space, time, and consciousness may exist in other universes, but it also exists here and now, and that makes it remarkable. The multiverse also raises profound questions about identity and continuity. If there are countless versions of you making different choices in parallel realities, which one is the real you? The answer, according to multiverse theory, is that they all are. Each version experiences themselves as the continuous, authentic you from their own perspective. Your sense of being a unique individual persists even in a reality where infinite variations of yourself exist. This connects to questions about consciousness itself. If the multiverse is real, consciousness might be far more fundamental than we typically assume. Rather than being a rare accident that emerged from complex brain chemistry on one planet, consciousness might be a basic feature of reality, the way that information patterns experience themselves from the inside. Some philosophers and physicists suggest that consciousness might be what selects which branch of reality we experience in quantum many-worlds, or what determines which mathematical structure we find ourselves embedded within. From this perspective, consciousness isn't produced by the universe, but rather helps create the universe we experience. The ethical implications are equally profound. If every possible choice you could make plays out somewhere in the multiverse, do your decisions matter? The answer is emphatically yes. While other versions of you might make different choices, this version of you, the one making decisions in this reality, bears full responsibility for the consequences of those decisions in this branch of existence. Moreover, if consciousness is indeed fundamental, and if every conscious being's experience matters equally across all branches of the multiverse, then ethics becomes not just about reducing suffering and increasing well-being in our observable universe, but about the total impact of our choices across all possible realities. Multiverse theory also offers a unique perspective on meaning and purpose. In an infinite multiverse, every story gets told, every possibility gets explored, every potential gets actualized somewhere. This doesn't make individual stories meaningless, but rather suggests that the universe or multiverse has an inexhaustible creativity, constantly exploring every possible way that matter, energy, space, time, and consciousness can organize themselves. And on that note, we've reached the end of our journey through the multiple realities that might exist beyond our everyday experience. We've seen how simple analogies like soap bubbles and library books can illuminate some of the deepest and most challenging ideas in modern physics. We've explored how cosmic inflation might create infinite pocket universes, how quantum mechanics might split reality into endless parallel branches, how mathematics itself might be the fundamental substance of all possible realities, and how information encoded on cosmic boundaries might give rise to entire holographic universes. Most importantly, we've seen that these aren't just abstract ideas, but theories grounded in our best understanding of physics, supported by mathematical frameworks, and potentially testable through careful observation and experimentation. Thank you for joining me on this exploration of infinite possibilities. I hope these ideas give you something wonderful to contemplate as you drift off to sleep tonight, perhaps dreaming of all the parallel versions of yourself exploring their own cosmic mysteries and realities beyond imagination. Until next time, keep looking up at the stars and wondering about the deeper mysteries they might hold.